but I'm gonna walk through it with you guys. So here we have the phase diagram for 50/50 PB and magnesium alloy. So part A wants to know at what temperature does the first solid phase form. So first we need to go to the 50 mark, which is right here. And then we're going to start at 7 degrees Celsius. We're going to make a line and go over. And essentially this is where it meets. And they kind of have an outline already. This dark line here. So it's like red or orange or something. And so they want to know what temperature the first solid phase form. So we're going to line from 700 degrees Celsius to the 50 weight percent. So then we just go down until we hit this point here. And so upon cooling from 700, the first solid phase forms at the temperature at which the work line at this composition intersects with the alphase, or the alpha alphase, which is at about 560 degrees Celsius, which is what they say here. So we find this intersection, it intersects at the L, alpha plus L region. If you need to find that temperature, you just simply gotta go like this, just make a line across over there, and you'll find that line. For part B, they want to know the composition of that solid phase. And the composition of that solid phase corresponds to the intersection with the alpha plus L, this point here. Alpha plus L phase boundary, with a tie line constructed across the alpha plus L phase region at 560. So in other words, you'll end up with a 21 weight percent of lead and 79 weight percent of the magnesium. So in other words, so they're looking at this tie line here in yellow. So if you go, yes. So here's the result. You're saying that the first solid is 21 weight percent here. And if we bring this one down, it should hit about, or it should equal, I should say, 79% of magnesium. It's since they're basically a ratio of each other. In part C, you want to know at what temperature does the liquid solidify. And the complete solidification of the alloy occurs at the intersection of this same work line at 50 weight percent with the eutectic isotherm, which is about 465. So if we take out our red marker again, essentially we're going right here to the 465. This is where it becomes the, basically solidifies into that eutectic isotherm, so basically this guy. And if we draw a line so that we can visualize it. Still difficult to visualize, but that's about 465 degrees. And part D, they want to know the composition of this last remaining liquid phase. And to determine that, so basically the composition of the last liquid phase remaining prior to complete solidification corresponds to the eutectic composition. So this line here, where they kind of put it up. So at this point, which should be about 67 weight percent lead and 33 weight percent magnesium. Right, so above it you have basically the liquidus form. So basically it goes straight from liquidus form to the solidified part right at this point and at 465 degrees Celsius. So it doesn't go through the alpha plus L phase, it just goes straight from liquidus to the alpha plus magnesium to lead. So did you guys have any questions on this one? Is it, you mean, so are the elements different? Oh, I see. Wait, so, I'll take your peek. Oh, so it's this one. Yeah, so in this case, this will be liquid and then like a combination of solid liquid, and that was just solids. So depending on, I believe, yeah, this one's a little different from this one that I did up here. This one might be a little further into your homework, but the concept kind of still applies. So I'm wondering if we did something like that a little earlier or last week. And yes, you had a question? Alright, so kind of like how we went over last week, so you gotta pay attention to, well, so this guy here at the bottom. So for example, let's go to like this point here. So if I draw my line down, it looks like 65, but technically, according to the book, it says 67. So we would read that as 67% of the lead, but then you have to remember that magnesium is a part of that. So basically take 100 minus it by 67, and you end up with whatever that other part is. It should be, yeah, 33% of magnesium, for example. Any more questions on this one? Okay, so yeah, so I'll try and go through this part a little quick. Okay, so for the next set of questions in your book, it discusses basically the development of microstructure and the eutectic alloy. So depending on composition, you'll have several microstructural types that are possible during slow cooling of alloys in a binary eutectic system. So the first case applies to compositions ranging from a pure component to the maximum solid solubility of that component at room temperature. And essentially it explains what happens when you have an almost pure metal that cools from a liquid state into a solid state. So I believe that's what this image here on the left is basically saying, or how you would read it. So key takeaways from that, you gotta look at the composition range. It'll apply to the very low concentrations of the secondary element. So yeah, so it's definitely this guy here that we're talking about. So the alloy, if you go up to the 400, it'll start off as completely liquid, and then as you basically start to cool down, you start crossing over the liquidus line. And that's where the solid alpha crystals begin to form, and then that's where you have phase transitions as you continue through the alpha region. And the amount of solid basically increases with the liquid as the liquid amount is decreasing. So as you're making your way down that line. And the second case considers is for composition between room temperature solubility limit and the maximum solid solubility at the eutectic temperature. So it should be this guy here. So case 2. So essentially, as the alloy cools, so we're starting off at this higher temperature again. As it cools from a liquid, it'll form a single phase solid solution. So in the alpha phase, or the alpha grains, and at this stage, it'll behave exactly like the low concentration alloy. It's crossing over into this L plus alpha. And pretty much as you go through these different phases, you end up with different, basically either liquid or solid forms of that material composition, essentially. And unlike the first case where the alloy is basically the same, it doesn't really change. In the second case, the alloys end up with a two-phase microstructure consisting of a matrix of alpha grains with some beta grains in there. Beta phase inclusions inside the structure. I don't really sort about that guy there. And here it kind of talks, it mentions the other microstructural developments of eutectic systems. I think there's, like 4 different ones. So in this one, in the third case, it involves the solidification of the eutectic composition, which is around 183 in this case. That's what they call, I guess, the critical temperature. So at that point is where the entire liquid volume starts to transform. And in this case, I believe it's, so it's your lead and SN. And because the liquid must split into a lead-rich phase, or which is alpha, and a tin-rich phase, which is the SN or the beta, the atoms are going to physically move, and it's going to lead to atoms diffusing toward the alpha regions, while the tin atom diffuse toward the beta regions. So once you move across that line, you end up with this characteristic grain structure here in the alpha, in the alpha plus beta region. And then for the fourth case, the fourth and final microstructural case of the system, it basically includes all compositions other than the eutectic that when you cool it across the eutectic isotherm. So again, as you cool it from the liquid phase into the alpha plus L region, which is above the eutectic temperature, the solid alpha grains are going to start forming, and you can. This is called the primary alpha phase because it developed first. And by the time the temperature reaches the eutectic line, which is at that 183, it's that guy there. The remaining liquid is going to reach the eutectic composition, which is 61.9%, this guy. And then the moment the temperature drops below the eutectic isotherm, all the remaining liquid is going to transform instantly into the eutectic structure, which is that guy. So essentially this is what the question I'm going over, this is essentially what they were going over from your slides, is these different microstructural developments. Okay, for the question, I think this one is also based on homework as well, or very similar to homework. So it reads, so they want you to consider a hypothetical phase diagram for metals A and B. They don't mention specifically what metals, it's just, so they're mentioning that it's similar to the lead tin system, which is in your book figure 9.8, but in our case it's going to be hypothetical because they want us to think about it a little more, or just use the equations that are provided so we get the hang of it. So assume that alpha and beta phases exist at the A and B extremes of the phase diagram, respectively, and they want us to also assume that the eutectic composition is 47% of B and 53 weight percent of A. And they also want us to assume that the composition of the beta phase at the eutectic temperature is 92.6 weight percent of B and 7.4 weight percent of A. And they want us to determine the composition of an alloy that will yield primary alpha and total alpha mass fractions of 0.356 and 0.639 respectively. So feel free to start working on that now. I'll go ahead and put it together and show you guys how to do this one. And so I should probably introduce the equations to you. So the first equation is just the lever rule expression for computation of a total alpha phase mass fraction. I think we kind of touched on this in earlier questions for the chapter 9. And then the bottom one is kind of similar, basically the same thing, but it's like alpha Orion, computation of primary alpha phase of mass fraction. Yeah, so one's for alpha prime, one's for alpha, but I'll explain what those are. So the primary alpha and, or I should say total alpha phase mass fraction is this guy, and essentially this is this guy. You can kind of see where it's going. I'll go ahead and go over with you guys. So they gave us the hypothetical eutectic phase diagram. In this question, they didn't necessarily provide the diagram, but we could pull it up. Technically, figure 9.8 to help you visualize how to kind of go about solving the problem, but in this case, it's just computation. Basically, this guy is here. And they gave us the composition of the eutectic phase, which is 47%, so basically this guy. They gave us the composition of the beta phase, which was at 92.6%. And they gave primary alpha and total mass alpha mass fractions, which is these respectively. I have those written out already. And so essentially for this problem, we're just utilizing the lever rules that we have here off to the left side. The original composition divided by the beta composition minus the alpha composition. Actually, I'm just going to write about these. So now if we plug in our values for the total alpha phase of mass fraction, we'll end up with this value here, 0.693. Is equal to 92.6. We don't know the original mass composition. Divided by 92.6 minus the alpha composition. And then for the alpha prime total alpha mass fraction. That is essentially the eutectic composition minus the original divided by the eutectic again minus the alpha. So if we plug that in, what we'll be using this here, 3.856 is equal to 47 minus the original composition divided by 47 minus the alpha composition. And we kind of have a theme going here because if you guys noticed from homework and other questions that we've done during recitation, we got two equations, two unknown things going on again. So essentially what we're doing is so that we can find the original composition and the alpha composition. We basically just solve for these. Or we can use them both together to solve for each of those variables. And if we solve those together, we should end up with a C naught that is 13.6 weight percent. Actually, right, so they just wanted the composition of the alloy. So in this case, we would just stop at the C naught, or the original composition of the alloy. As you solve this, you can also find your composition of the alpha phase, which they don't give it, but you get the idea. Basically, if you solve for one, you can easily get the other one. And basically, that's how we will approach this problem. So we have first, I guess I'll go over first. First of all, assuming that the alpha and beta phases exist at the A and B extremes, that's just to make sure that we don't misinterpret what they're asking us in the problem. And then the key information that we underline to help us, I guess, outline what's going on in the problem, which is the eutectic composition, that 47 weight percent of B, and the beta phase at the eutectic temperature, which is that guy, at 92.6 weight percent. So we know those, we wrote those down. We also wrote down our primary alpha and total alpha mass fractions, respectively. So those two are down there. And pretty much as we, looking at context clues and whatnot from the problem, we would understand that this is basically a development of microstructure and eutectic alloys question. Very long title, long thing to remember. So once you list out your givens in this one, it may not jump out to you right away, but essentially you need to remember your level rule for these two, the total alpha phase and the primary alpha phase. And then that's when we'll start working on the problem here. You plug in your values, and then you'll notice that you can't figure out your original or your basically your C naught. Can't find this one because you're missing also the alpha phase. You'll learn that it's a two equations to unknowns. You can put those two together to figure out where your C naught is, and then that will help you get to your C naught. Any questions on this one? So the two equations to unknowns came back, and then actually I'm going to double check and see what question you have left. There's about 4 questions left, so I'm wondering. Okay, Okay, so next question, let's quickly go over this one. So they mentioned for 68 weight percent zinc, 32 weight percent copper alloy, there's sketch of the microstructure that's going to be observed for conditions of very slow cooling at the following temperatures, and they list them, and they want us to label all the phases and indicate approximate compositions. So essentially, we need to find where we have a 68 weight percent of zinc, which is about right here. Then we're going to start at 1,000. All the way over. And then we're drawing it down. It's not a very big line. Okay, so then the first one. Essentially, at this point, kind of just looking at it. So at 1,000 degrees Celsius and 68 weight percent, we see that we're in the liquid phase. So for that one, that one's in the liquid phase. If we drop down to 760, which I'm gonna guess is like somewhere in there, we're gonna get that. It looks like gamma plus L phase. And then you kind of see how it's going. So, over, that looks like delta phase. And then the last one they gave us was 400. And that's what they call the gamma plus epsilon phase. So to visualize it a little bit, in the 1,000 degree case, it's just a liquid phase, it's just the 68% for zinc. And then if we go to 760, here's going to be your 67% of zinc, but you're also going to have a liquidous phase that's 75% of zinc. And at 600 degrees Celsius, you have kind of like this microstructure going on, which is gamma. At 68% of this is zinc. And at 400, you have these tiny microstructures inside of these larger rings. And so this guy, that's our epsilon phase with a 78%. And then kind of in this bare spot, see 70% of zinc. That is gamma. So any questions on this one? So as far as answering it, it's just this guy here. You would first find your 68 weight percent composition, and then you just go through the different temperatures essentially. And you draw a line from your temperature over to the line, and then you figure out where it lands, and then that's how you would know at that temperature what microstructure it has. So We all good on this one? Okay, cool. So quickly, I'll try to touch on this very briefly. Essentially, this is kind of the same thing that we learned out before, but in iron carbon alloys. In the interest of time, because essentially we're kind of doing the same thing, but we're just doing it with iron carbon alloys to determine the microstructure and stuff. But this section is in your book if you guys are interested in reading about this one. Go ahead and read about this. But essentially we're doing the same things that we did in the other sections. Instead now it's just iron carbon stuff. Okay, so this question states, what is the pro-ejectory phase for an iron carbon alloy, and what's the mass fractions of total ferrite and total cementite, or 0.92 and 0.08 respectively, and why? And I know for this question they're using this W alpha prime or the Lorentz expression for the pro-ejectory ferrite mass fraction. So I'm going to quickly show you guys how to go through this one. Okay, so in this problem, they gave us the mass fractions for the alpha, which should be this right here, 0.2. And they also give for this guy here as well. For the iron carbon alloy, and they asked us to specify the pro-ejectory phase. So to do that, we have to use this expression here that we have off to the side. So let's go ahead and plug this in. So it's 0.92 is equal to essentially which is our composition of the iron through carbon phase subtracted by the original composition. And we have the iron carbon phase again, but subtracted from the alpha. I'll go ahead and put those values in. This one's going to be 6.7. Wait, did it mention? Strange, they don't mention where they got this 6.7 from. I'm assuming they would get it from, or 6.7. I'm not sure exactly where they got that value from. So they took that for their composition of the iron carbon phase, subtracted from the original composition. And they also subtracted that from the phase of the alpha, which is 0.22. Okay, so they're getting these from, basically from your text, or so from your text. These are different compositions, or the listed compositions of the iron carbon phase and the alpha phase. So you can find those in the phase diagram, which I'm sure if we look in here, we should be able to point out those values inside of the slide. And so here, if we solve for C naught, we should end up with the alloy composition, which is 0.568% carbon. Therefore, the proutectoid phase is alpha ferrite, since the C naught is less than 0.768%. So essentially, they're answering that Y part at the end of that question. So since this here, 70% carbon is less than the alpha ferrite, which is 0.76% carbon. That's how we know that it's proutectoid. Okay, so any questions on this one? So again, the composition of the iron carbon and the composition of that alpha phase, that's from your phase diagrams. Those are like listed values at the cement type. So those values are listed in the phase diagrams, like in your text and stuff. So you use those values and plug those in there. And we're trying to find basically the composition of the original alloy. And we ended up with this. And then this is our justification basically to tell ourselves that this is proutectoid because of this expression here. Since it's less than 0.768% carbon, we know it's proutectoid. So almost done. So this one kind of the same thing, but they're mentioning I don't know how many grams of proutectoid ferrite is formed, how many grams of proutectoid ferrite, and cement types as well. So this one is C2N. We're just going to use that equation to come up with the composition. And then from there, like back calculate it out so that we can get mass. So kilograms, US 99.68%, Fe 40%. Carbon alloy, that's gold. So the equation that I pulled for you guys here, we would use that to solve for the alpha prime with the alpha prime, the proutectoid ferrite mass fraction, and then basically multiply that mass fraction that we get to this mass here, and that will give us in kilograms the real proutectoid ferrite form. So basically, that is going to be, so our W alpha prime is going to be equal to 0.49. And if we write that out, that 0.49 is equal to 0.76 minus the C prime time over 0.74. So essentially this right here. And our C naught prime should be equal to 3.49. So here. So essentially we'll multiply this mass fraction to the actual mass. Then this will give us 0.98 kilograms, which is the mass in kilograms of the protein to a ferrite form. And yeah, so essentially we're doing the same thing as this one as well. So part B, kind of the same deal. So for part B they're using just alpha, so not alpha prime. And that's going to be nice. Oh, my bad. So I didn't do this one. So we're using the W alpha prime equation, but this is what it should write out as W alpha prime. It's the 0.76 minus the 0.4 over the 0.74. Yes, like the one I just circled. And then that's how we get the 0.49. And then we'll do 0.49, and that's how we get the mass. For part B, we're using the alpha equation, which to remind ourselves is this guy here. So when we plug that in, so just like in the last problem too, we actually used this one last problem. Minus 0.022, 0.94. Then you plug it in at the 0.94 multiplied by 2 kilograms. And we'll get 8 kilograms. So that's part B. Part C is essentially the same deal as well as part B, but you are trying to find the mass fraction of the iron carbon, the Fe3C. So I'll write that out so you guys can see it, and I want you guys to put in those values. So essentially, if you solve this for part C, you'll end up with 0.057, and then same deal, multiply the 0.057 to the 2 kilograms, and you'll end up with 0.14 kilograms. So with this one, you definitely need to understand your prototentoid and the iron carbon phases, the alpha phases, understanding from your text like what those values are, so that way you can effectively use these formulas. So any questions on this one? Pretty straightforward, kind of just plug and chug, but you also have to remember your, again, like I was saying, your phase values from the iron carbon alloys phase diagrams. And then very quickly, let's try to do this one. So this one is saying the mass fraction of the eutectoid sintite in a iron carbon alloy is 0.14. On the basis of this information, it's impossible to determine the composition of the alloy, and if so, what's the composition, and if it's not possible. We got minutes to explain why. So kind of long. So the problem is asking whether or not it's possible to determine the composition of this hydrocarbon alloy. For the mass fraction of eutectite, you'll see it as 0.104. And if it is possible, it wants to calculate it. And based on this problem, it is possible to determine the alloy composition. And apparently there's two possible answers. But for our case, since we're not interested, I'll show you guys the one way of going for it. So for the first, the eutectoid cementite exists in addition to the pro-eutectoid cementite. So for this way, then we'll show you guys how to solve for it. The mass fraction of the eutectoid cementite is just the difference between the total cementite and the eutectoid cementite mass fraction. So I'll show you guys what it means. So essentially we're using this guy here. And so now we can write this out kind of like in the equation that we've seen already before in that expression. So essentially this part here so we go to the original mass fraction minus alpha. Fraction of the iron carbon subtracted from your alpha, but minus the original mass fraction minus 0.76 over 5.94. So essentially, if you so they didn't put in the values just yet. So that C alpha is going to be 0.022 divided by the 6.7 minus the 0.022. Subtracted from C naught. Minus 0.76 over 5.94. And if you do the math on that to figure out your C naught, you should end up with, or sorry, no, I believe we're solving for, oh no, okay. So I believe this is, yeah, your Fe3 carbon double carbon that they solve for, I believe, that's it. I believe it is. And so, yeah, so I think this part, it should be given if you put together. So then, at this point, we can solve for C naught. Once you figure out this guy here, you can find your C naught or solve for it, and that C naught is going to give you 1.1%. So very quickly, because this first part is a little confusing. Don't know how I did that. So the other way to solve it, which is probably going to make way more sense to you guys, is just using this guy here. I won't plug in the numbers because we're basically going to get the same answer, but I'm pretty sure this is something that we already worked with in the earlier examples. So I'm just going to put it up here so that you guys can reference this one. So, based on your phase diagrams and whatnot, you should be able to find these values. And then the only one missing should be your C naught with the same answer, the 1.1%. This one, yeah, it's confusing. So yeah, it's using different basically microstructure alloys to solve this one. So I guess this one is Hypo-Eutectoid, and then the other one is, yeah, this one's a little bit of a mess. Let's try and quickly write this one. Eutectoid cementite was this one. Cementite. Technically, the answer for this one is going to be a little bit different, but it's going to mean the same thing because you're working with in the phase diagram and whatnot. Okay, so that's the last of chapter 9. Question on this before we move on to some chapter 10 stuff. Okay, cool. So I'm handing it off to Mehdi, and then he's going to talk to you guys about chapter 10 stuff. And we also have chapter 11 for you guys. It's super short, not really a whole lot to help you guys with. Like two math questions or whatever. But it's not hard math.
Okay. So good afternoon, guys. We're going to go over chapter 10, but before that, I'm assuming based on the syllabus, just started chapter 14. Or you are still okay. So that's why we are kind of just rushing everything to catch up with the class. So we wanted to, before those things, we wanted to go over and review chapter 10 and 11, so we would have enough time to solve the assignment for those two chapters. Okay, so let's start with chapter 10. So this chapter is about phase transformation, right? So in the chapter 9, we learn about phase diagrams and how like one phase can transform into other phases. But here we're just gonna focus on the phase transformation process itself. And the process can be broken down into two steps. The step one is nucleation, and the second step is the growth of those nucleons. And for the nucleation itself, we can classify it into two different classes. So we can have homogeneous nucleation or heterogeneous nucleation. What's the difference? The difference between these two is, so in the case of homogeneous nucleation, the nuclei form uniformly everywhere in our system. But when we have like heterogeneous, the nuclei tends to just form in inhomogeneous, for example, like in dislocations in our system, in our material, things like that. So it was just an introduction, but the main thing we're gonna learn is, so let's focus on homogeneous nucleation. If you took thermodynamics before, you are familiar with delta G. So, transformation basically occurs spontaneously if delta G, or the free energy, has a negative value. So how do we calculate the free energy in our case, which is nucleation? So basically it's the sum of two terms. The first term, this guy here, is about the bulk energy, volume bulk energy. So that's why we have the volume of a sphere times by delta GV, which is our volume bulk energy, or just the volume free energy. And we basically are assuming we have a sphere as our nucleus. The second term is about the surface energy. And again, we are multiplying the surface of a sphere in what we showed with gamma here, which is just the surface energy concept. So, this is our delta G. And we have this delta G with the green dashed line, which is the sum of these two terms. So this one is the blue line, and the surface energy is the red line. And you can see this one is negative, that one is positive, but this one has R cubed, but that one is R squared. So, which means eventually our delta G is going to be negative when the R grows larger. But in this context, we have two important values, or the critical values, R star and delta G star. Basically, it means if the radius approaches this R critical value, delta G changes in a way that the rest of the nucleation happens spontaneously. So if a nucleation happens but the R is smaller than R star, it means it's just not going to happen any further. So I guess in our text it calls it not a nuclear but a barrier. But so that was the explanation of the logic behind these two values. The important thing here is that's how we calculate the R star, And that's how we calculate the delta G star. Okay. So this is just the continue of the previous slide. So we can write down the delta GV as this related to the temperature, because here we don't have the temperature, but if we just expand delta GV, we can relate our critical values to temperature. And if we just plug in delta GV in those formulas, these are the formulas we get here for our critical parameters. And okay, so that was about nucleation. Let's talk a little bit about the growth as well. So in the growth, we have a rate, which actually we kind of show the growth with a figure like this, in which one axis is just the time, the other is the fraction of transformation, or the transform fraction. And there is a rate, and by convention we show the rate as 1 over the time when half of the system is just transformed. And we have a very important equation here of Raman equation, which is just showing how this y, which is transform fraction, relates to the time, and kn here is just parameters for the system. But this but this figure on the left depends on the temperature. So for different temperatures, we have different curves. So let's focus on the first problem here. So it says if copper, which has a melting point of that, homogeneously nucleates at that temperature, calculates the critical radius given values of that and that for latent heat fusion and surface free energy. Okay, feel free to think about it and solve it. We're going to go ahead and solve it together because we don't have time. So this is the formula I just showed you here, up here. So what does it mean? Look, the latent heat of fusion, it's this delta HF. That's the latent heat of solidification or fusion. And melting point Tm is this number up here, 1085, and the gamma is the surface energy is also given. So the rest is just plugging in the numbers, right? So we're just gonna plug in the numbers here. It's going to be equal to 2 times 2. Remember, everything should be in Kelvin, so we have to transform convert our temperature to Kelvin. sense? So it was just a simple formula. Change it to Kelvin, but here, if you notice that I didn't like convert it to Kelvin because basically we have two temperatures. And it doesn't matter if you do it to the subtraction of Kelvin or the Celsius. It's gonna be the same. Okay. If you don't have any questions about this one, we'll go to the next. It says, so compute the rate of some reaction that obeys overwhelming kinetics, assuming that the constant N and K have values of 3 and 7 times 10 to the minus 3 respectively for time expressed in seconds. Okay, the Avrami, we just saw it. So this is the Avrami equation. Okay, so we need to find the rate. What is the rate? Is 1 over t half. And the t half means the time the system needs to, half of the transformation, half of the system has been transformed to the new phase, right? Based on, let's look at this one. Here we can. So this is the fraction transform, and this is the time. And the rate is 1 over the time when half of the system or half of our material, the phase, transform into the new phase. So basically, to calculate the phase or the rate, we have to calculate the T half. And we know our system obeys the Abraham mechanics, right? It means we can mess with that equation. So this is here, that's the Abraham equation. But again, we have like exponential form that like it, we want to make it kind of like linear. But here in this case, we want to solve it for t, because we are looking for this t half. So we have all the other parameters. We are given the n, the value of n, the value of k. And we know this is going to be half because we are looking for t half. Basically, we have all the other parameters. So we have to just rearrange the parameters to solve for t. And if you do that, that's the final form you get out of this equation. Then you just plug in all the numbers and you calculate this. And to find the rate, well, it's just 1 over this number, 4.63. So, and here, so rate will be 6, which is equal to 216. Okay, so last question about this section. Again, two equations from announced, just wait for a minute. Well, this one, I believe this one is very similar to
Got busy?
homework.
Yeah, I got this.
So,
know.
let's read the question together. The candidate of
Have fun through
austenite to pure
We can all try.
transformation
We're
obey
sure
the
of
Abraham
Yeah.
relationship, the relationship we just
Yeah.
saw. Using the fraction transform
Great.
time
Back
data
into the
given,
grind.
determine the total time required for 95%
You as well. Have a good
of
small
the
break.
austenite to
You too.
transform.
Alright.
So right we know is two equations, one now is go here, we already know the fraction transform, which is y in the Abraham equation, and the t. The equation itself is just this one. So minus k t. And we are asked to find the time when our y is 0.95. What is the time here? That's the question. So to solve that, first we need to find n and k based on the table given here. How we can do that is just, a bit of math. So again, we have to transform the equation in a way that we can solve for k and n. So if we do that, we will have So I know it's very annoying, but yeah, that's the way we transform the equation to this form because we want to find k and n. So let's get back to our table. So now if we plug in the information we are given in this table, so which means one time we plug in y as 0.2 and t as 12.6 and we get something like this. So I'm gonna add here plus this one. We get two equations from like this. Okay, so this is our two equation. And if we solve this system, we get n equal to 2.0. So now we have now we have n and k. We just again we have to go back to the Orthogonal equation. And what are we trying to solve for? We want to find the time or the t when y or the fraction transform is equal to 0.95. And if we do that, so I'm going to write that over here. Just want to include this question because I think that's probably the most hardest question someone can design from this chapter. is this section. And you have similar position in the middle as well. So again, just be familiar with these forms of, the Avram equation. These two. This is when we want to solve for t. This is when we want to solve for example, k or n. Okay. Any questions? So, we are moving to the next part, but this is also important. Isothermal transformation. Right? So far you have seen phase diagrams, but well, basically, I believe you have the concept supercooling and superheating in your slides. Well, the phase diagrams we have seen in the previous chapter, they're only valid when we have equilibrium, right? It means the rate of cooling or heating is very, very, very slow, which is basically not very practical. So in reality, the rate of cooling might be pretty fast, actually. So in those cases, what happens is we don't follow that, that structure or that microstructure explained in the previous chapter. For example, this is just one example for eutectic iron carbon system. So if you have a eutectic iron carbon system, it's showing, well, this is like the curve we just saw, time and y. But here, if you can like show it in another figure like this one as well, right? That's the eutectic temperature, the orange line. So in the previous chapter we saw below that temperature we don't have austenite anymore. But in reality, if you cool it pretty fast, the system doesn't have enough time to transform all the, for example, all the austenite to another phase. That's why we have something like that, right? If you cool it down, for example, to 600 and keep it steady at that 600 degrees, that's how the system transforms over time. It means austenite is gonna change, the 50% of our austenite is gonna change to pyrrolite after this period of time, probably a couple of seconds. And after 10 seconds, approximately, all the austenite is gonna change into pyrrolite. So it depends on temperature. And the lower the temperature, that time is gonna take longer. So that's the main concept behind these isothermal transformations. So let me see. It's again the same thing. So, for example, you cool down your system to this temperature here around 620 degrees. So at here, before this line, you have totally just austenite microstructure. But when you hold your system at that temperature for enough time, and it starts to form some pyrrolite structure. And again, if you hold it enough, all the austenite is going to turn into pyrrolite. So we can have those figures or those plus graphs for different composition. So remember, here we have time and temperature. So we cannot show several composition or various composition in this way. So we can draw this graph only for one composition. For example, this is the most common for the eutectic composition. But if you have a different composition, non-eutectic composition, it should be eutectoid. A non-eutectoid composition, the plot could be different. For example, so this is the eutectoid composition, right? And 0.76 here. But if you have something at this red line, it could have a totally different figure compared to eutectoid composition. Okay, so these questions are very short, and so let's work on the first question together. Consider the following isothermal transformation diagram for the heat treatment designed by the segment line labeled ABCD. So this is the ABCD. This is the line or the heat treatment that our system is passing through. From the list below, which is not applicable here, but okay, we have to find microstructure after the microstructure of this system after the heat treatment is done. So we start at point A here, and we end here. So we want to know when we are at point D, what is the microstructure of our system? So let's look at this chart together. So we start here, and we know at that temperature, we only have austenite here. So this part up here is only austenite. So at point A, our system is made up of totally just austenite. When we move along this line here, and in a temperature probably like 720, 730, something like that. So we hold it at that temperature for 1,000 seconds, right? So during this transformation, so we reach the temperature to 720, for example, and we hold the system at that temperature for 10 seconds, for 100 seconds here, because that's logarithmic. Say the scale here, so this is 1, this is 10, 10 to the power 2, 10 to the power 3. So be careful with those units. So before we reach like the 10 second, which is here, just slightly before that, our system is entering another region in this diagram, which means transformation is happening. So what is this region? This is A, which is austenite plus ferrite, which is just it's the same as alpha ferrite, right? So our system is starting to make, some of the austenite is starting to transform into ferrite. But after after 1,000 seconds, and something is just should be known as you should have specified the. So this is the eutectoid temperature, not mentioned on the figure, but it should have specified that. This is the eutectoid temperature. So basically, we are in the vicinity of the eutectoid temperature. What happens is, when we hold our system at that temperature, after a while, some of the austenite turns into pro-eutectoid ferrites, and the pro-eutectoid means we not past the eutectoid temperature. But below that, so this is like around 50% of our austenite has been turned into ferrite. But after that, the remaining austenite, whatever it is, because we just cool the system down pretty quickly to the room temperature, whatever remains is going to turn into martensite. Just let me take that. I think there's something. Wait, there's something wrong with this one. Not wrong, but I think there is, something is missing on this figure here, because okay, yeah. We have pro-eutectoid ferrite and martensite here, but we cannot tell the percentage of these two. Okay, now it makes sense. I thought we have to find the percentages as well, but we don't have to, because we are not able to find those percentages here in this with this diagram. So this is fine actually. But are you familiar with, or do you remember like what happens when so let's go back to this diagram for eutectoid composition. So the thing is, we have austenite here. Okay, we have austenite here. If we cool it down until this temperature, the austenite is going to turn to pyrrolite. This is just a quick review, if you forgot it. But below this temperature, austenite is going to turn to bainite. What's the pronunciation of that? Let's say bainite. But there is a temperature, if you cool it down very, very, very fast, to a very, very low temperature. So for example, you start at a temperature like above 720, and if you cool it down to, for example, at 200 degrees, it's going to turn into martensite, which is shown here by M here. So I just wanted to review that with you guys. That's why we have martensite here. It's shown with M. Okay. The next question is just show this idea better. Okay, so we just have a couple more minutes. Let me just show you this, then we're almost done, I guess. So it's again the same thing. We start at the temperature above here, and mentioned like our system is remained at 760 long enough to achieve a homogeneous austenite structure. But in the first scenario, if we rapidly cool it down to 600 to here, and hold it for 4 seconds. 4 seconds, this is since there is a log scale, so 4 seconds I assume should be something around here. So if we find the intersection, so we will have something like this. And rapidly cool it down to 450 here, and hold it for 10 seconds. then punch it to room temperature. So 10 seconds, so we have 10 here, 450. Okay, so this is it. So then the room temperature, which is here. So what would be our microstructure? So we started austenite, right? At the 600 degrees, some of our austenite turns into perlite, but how much? 50%, right? Because this is the dash one, the dash one is the 50% one. And if you look at just the time scale, 4 seconds, it should be around here. So approximately we reach this 50%. So far, 50% of our austenite turned into perlite, right? The remaining austenite, what happens to the remaining austenite? It says we cool it down to 450. When we cool it down to 450, well, the perlite is not going to change anymore. So we're not going to do anything with that 50% perlite. But for what happens to the 50% austenite that we have? From that 50%, half of it turns into bainite. Does that make sense? So whatever is left from the austenite, half of that is going to turn into bainite. So that was the first step, right? In the first step, just consider it like that. So in the first step, let's say 50% of our system turned into perlite. So whatever turned into perlite, we just put it aside. We're not going to use that anymore. I mean, perlite is just stable. It's not going to change anymore. So for the further or for the remaining steps, we're going to just focus on the remaining austenite. So in this case, in the first step, we lost 50% of austenite. Not lost, but 50% of the austenite turned into perlite already. So what happens to the remaining austenite? We cool it down to 450 degrees and hold it for 10 seconds. So we start again from this axis, from 450 degrees and 10 seconds, which is this time. Well, this is again 50%. So whatever austenite that is left, half of it turn into bainite. Again, we just put aside the bainite because it is stable, it's not going to change, but we're going to work with the remaining austenite. What happens to the remaining austenite? It is quenched to room temperature, which is here. So whatever is left is going to turn into martensite. That's how we get 50% perlite, 20% bainite, and 25% bainite and 25% martensite. I hope that was clear because that's actually just the most important thing, how we interpret these diagrams. If you get that, then you will be good for the homework and the rest of this chapter. Any question? Okay, again, RB and C is very, very similar. These are these are very similar. It's talking about just mechanical properties. So the mechanical properties of our system will, when we move like this, it's going to be tougher, harder, and more strong. So martensite is more strong than bainite. Bainite is more strong than perlite, and we have two types of perlite. Coarse perlite, which happens when the temperature is closer to this detector temperature, so it happens in this area, find periodite which is here. And again, according to this, so this is gonna be more stronger than this one. And this one is more stronger than austenite. So, but the ductility is reverse. So austenite is the most ductile and martensite is the less ductile. That's basically it. And based on that, and the other thing is the more when this is for just one composition, but when we are comparing different composition, when we have more carbon in the system, it's gonna be more strong and it's gonna be more brittle. And based on that here, so this is like the hardest or the strongest composition because it has the most carbon from these. This has no carbon, it's just alpha, just ferrite, no carbide or cementite in the system. But from these three options, C has the most carbon, so this is going to be the hardest one, and this is the softest one. But what about B and D? You want to rank this based on hardness or softness. What about B and D? Well, they are almost like regarding the carbon content, they are almost the same. But the thing is, this one, so this, this lamella structure, we call it pellet, right? Previous chapter and this chapter. So this is the fine pearlite. I mean, this cementite beams or whatever you call it is. So you have better distribution of alpha and cementite, Fe3C. That distribution makes it harder. So that's gonna be our ranking. So this is the hardest, then we have D, then we have E, and A is gonna be the softest. This is very, very simple, so I'm not gonna solve it. But I guess I'm done. But for this chapter, I reviewed the most important things. I mean, the hardest part you may get confused when solving the question, but the rest of the chapter is very, very easy and so it should be good. Do you want to have anything for the chapter? So we're probably gonna change the due date for chapter 11, but just try to solve it because I'm pretty sure you can solve it. But most probably you won't have any problem solving the homework for chapter 11, but just in case you have some questions about that, we're gonna just extend the deadline. That's it.